Okay, here we go. Not what I wanted. What? What I was hoping for is you'd be able to access the practice test through that. I don't think you can. Sounds like you can't. So I, I'll mess with it. All right, here we go. So real quick, um, electric field versus magnetic fields. Electric field goes out of positive into negative. Magnetic fields go out of north into south. Okay, they're different. So they're similar patterns, but they're different critters. Okay, here you can have a single positive charge. You can have a monopole for an electric charge. We have yet to discover any monopoles going on in magnetism. There's always a dipole. You have to have a north and a south. Okay. Um, to make a magnet, you have iron, nickel, and cobalt are your three magnetic elements. They have valence electrons that, remember when you're doing chemistry, you're doing spins, electron spin. Iron, nickel, and cobalt have a couple unpaired spinning electrons. So like spin up, spin down, that creates a magnetic field. Some of theirs, like three of them, are like spin up, spin up, spin up. So there's a net magnetic field to those. Um, and so they form these domains, these crystals. They're like microscopic, but not crazy microscopic, like red blood cell size microscopic. Um, and if you can get the magnetic orientation of those magnetic domains lined up, you get a magnet. So here this will be random. Um, okay, so it's being ferromagnetism. So fun fact, the Earth has a magnetic south pole at the geographic north pole. We learned that last year, right? This is all okay. So we're going to use, so if you have moving charge particles, that creates a magnetic field. We have right hand, what I call right hand rule number one. Okay, you stick your thumb in the direction of current, your fingers go around in the direction of the magnetic field. Okay, use this, it works out great for a current with wire, sorry, a wire with current flowing through it. Okay, so which way is the magnetic field? Is everybody good with F? Out of the page, this is a circle with a dot, is you're looking at the arrow as the arrowhead comes out of the page at you. This is the tail feathers of the arrow, bless you, as it goes into the page away from you. Good? Okay. So is everybody good with out of the page? Here's a way you can visualize that. Pretend you're spinning a tennis ball on a string and you let go at point P. It's going to come out of the page towards you tangent to the circular path. Solid? Okay. Tell your neighbor. This one's going this way. This one's going this way. This one's going tangent to that. This one's going that way. The resultant of those is 3. Good? Correct answer is? Correct answer is E. Okay. Fun fact. Well, not fun fact. It's just application to this. If you've ever installed an invisible fence for your dog, it runs off the magnetic field coming off the wires. To have the part where it comes from your house because you have to plug it in somewhere, you don't want any magnetic fields going there. So what you do is you take wire and you go out and you go like you go out and you go around your yard and then you come back in to plug it in. These two fields, you actually twist these together and those two magnetic fields cancel each other out. You don't zap your dog. Cool. Okay. Okay. You can do this two different ways. You can use your just normal right hand rule, and if you're doing that, I would grab the part that's closest to you. So look at this part of the wire, grab it with your fingers going down. You can't grab it like this because you're looking at the inside. What you really care about is the inside of the loops. So your thumb is going uh, to the left. So that's the direction of current. That's one way to figure that out. The second way is what I call the alternative right hand rule number one. This is used anytime you have a coil or a solenoid or loops of wire. You can stick your thumb in the direction of the magnetic field and your current goes around in the direction that your fingers are wrapping around that coil or loop. Okay, that comes in really helpful when we talk about Lenz's law later. Alternative right hand rule. Okay, so there's that. So when you're dealing with, yeah, so um, I'll just give you a hint. The side with the bump is the positive. Okay. Tell your neighbor.
So this south line should be pointed down. The red one right there, the direction is
Okay. Current goes out of positive into negative. So we're going to grab this. The current's going around like this. Yes, and these, okay, your thumb's going up. That's the direction of magnetic field C. Okay. Tell your neighbor. Show them.
Oh wait, no, you
Okay, correct answer is B. Okay, your thumb is going to point in the direction of the north pole of the magnet. Okay, because magnetic field lines go out of north into south. Okay, that's on the exterior part of the magnet. On the inside of the magnet, it goes from south to north because it does full loops. Outside the magnet goes out of north into south, but on the inside it goes from south to north. Okay, your thumb points in the direction of the north pole of the magnet, so it's going in this way, out that way. Good? Okay.
You don't actually like need the metal in the middle, right? Just
Correct. Great question. Yes. Okay. So you have an electromagnet here, just with a solenoid. If you stick a piece of ferromagnetic material, iron, steel, or cobalt, most commonly is steel. Or sorry, steel is a compound of iron. If you stick that in there, that strengthens that magnetic field a lot. Okay, so you have an electromagnet, one that you can turn on and off. Okay? So, is this the way Doc taught you how to do right hand rule? Good. Okay, there's lots of variations out there. So, your okay. How do you know when to use right hand rule number 1 versus right hand rule number 2? The answer to that is if you have an external magnetic field, some other magnetic field that was not created by the object you're looking at. There will now be two magnetic fields interacting. You just care about the external magnetic field. So you're going to use your fingers, goes in the direction of the external magnetic field. Your thumb goes in the direction of the way things are moving. So velocity or current. Your palm pushes positive things. Okay, your palm pushes positive things. Negative hand, backhand, it's a negative connotation. You're backhanded. Okay, now here's the deal. Because Ben Franklin screwed up, and it was like positive things are flowing. We have this whole convention on positive things flowing. So current is positive things flowing. So you stick your thumb in the direction of current, you're pushing with your palm because he thought positive things flowed. Okay? If you're like want to like rage against the machine and like, oh, I'm going to be a realist, that's fine. You just got to really recognize that current goes in the opposite direction. Sorry, electrons flow in the opposite direction of current and they're negatively charged. Okay? But the convention is set up for positive things flowing. So stick your thumb in the direction of current and positive, your palm pushes positive. Okay? Good with that? Okay. So which way is the magnetic field going? Okay. To do these successfully, you need to lock in, you need to commit, you need to constrain one thing, okay? So I'm going to say velocity is going into the page. So I'm sticking my thumb into the page. So now I'm stuck. I've got to, okay? So now I'm going to move my palm because it's positively charged to face to the left. Fingers are going down. Good? Okay. Not during not during that's fine, but like during the AP test, you're no. Like that would be cheating.
What if we do it like during the AP test? Like the AP test starts and then like
Listen,
first like 10 seconds they have to write it down.
I don't know what the proctor. That would be a proctor call, and I don't know who's proctoring. Okay, give this one a shot. Okay, correct answer is negatively charged. D. Okay. Good with that? Left. Okay. Back of the hand. Use the back. Okay. Correct answer here. G. There has to be some component that is perpendicular to the magnetic field. Has to be some component that is perpendicular to the magnetic field. Okay. So if you have this, then you need to. Okay. So the equation. I should look up what the equation sheet said. The equation sheet. Didn't do that. The equation sheet had it. There it is. Equation sheet says, okay, your equation sheet says this: magnetic force is equal to Q V cross B. Okay. Memorize this: Q V perpendicular B. One of the components, either B or V, needs to be the component that is perpendicular to magnetic field. Or you could flip it and find the component of magnetic field that is perpendicular to the velocity. Anytime you see cross product, that's one of those vectors needs to be the perpendicular component. Okay? So you want that. That's V perpendicular there. Okay? In some textbooks, you'll see sine used a lot. Don't memorize that. That only works when the angle is between the magnetic field and the velocity. And sometimes they can throw the complement angle and say 50 right here, and then you're hosed. Okay, so this is a better way to remember that. Good? Okay. And so here, you would stick your thumb in the direction of the perpendicular component into the board, because it's negatively charged. Good? Okay. What happens when you've got a big magnetic field over time? What's going to happen? This thing's free to move. You're shooting it to the right. It's going to be forced is the best part. Rude. Okay, so as you do this, it's going to play the role of centripetal force and always acting perpendicular to the direction of. You good with that? Okay, so anytime you have a circle, you say, what's playing the role of centripetal force? Magnetic force. Okay, and so then you go mass times speed squared over the radius over magnetic field times the charge times velocity perpendicular. And you just run with it. Yes? Okay. So you get some cool stuff like Aurora Borealis, Northern Lights because of that. Did that last year, right? Okay. You also particle accelerators. That'd be cool, but no. Severely lacking funds and space. All right. So a velocity selector. This is a very this is like all over the place in introductory physics. Okay, it's a special case scenario that we shoot a charged particle in a region that has both a magnetic field and an electric field. And we do it in such a way that it shoots straight through. Okay, so in order to get it going straight through, we know that the force, so if this is positively charged, the electric force on this is going to be going to the left. In order to cancel that out, I need my magnetic force to be in opposition to that. Okay, so this is going down, it's being forced that way. Okay, so these need to be equal to each other so that the sum of the forces are equal to 0. So you have electric force is equal to magnetic force. This is equal to electric field times the charge. This is equal to magnetic field times the charge times the velocity perpendicular. Charges go away. That scenario happens a lot. Okay, in AP or introductory physics classes. It just does. It's just, okay. And they have it, all right, yeah. Have a conversation.
I used to vote in. My charge, I use the right foot, so I find it's much more
Correct answer is Try it. Try with the other one. There it is. You're like you concluded A or B. Try with the other one. It works. Remember to use. Okay, so if it's negatively charged, the force is in the opposite direction of the electric field. If it's negatively charged, remember to use the back of your hand. Everybody convinced? Positive. Force is going, the electric force is going down in the same direction of the electric field. The magnetic force is going up. Palm pushes positive. If it was negatively charged, the electric field would be going, sorry, the electric force would be going in the opposite direction of the electric field. And you are holding your hand the same way, but it's being pushed with the back of your hand down. Either way works. Could be a really good AP multiple choice question. I don't know. Okay. Correct answer is I want the magnetic force to go which way? I want the magnetic force to go down. The opposite of the electric force. The electric force is going up. Yes? Sorry, if this is positively charged.
So the electric field is going to push the electron down.
Sorry, didn't know it was, sorry, electrons. Sorry, didn't read the question. So the electric force is going down. Okay? So I need the magnetic force to go up. So I'm sticking my thumb in the direction of the velocity. I need my back of the hand to go up because it's negatively charged. Yes? Out of the page. D.
Would it be any different if it was
It would not. Okay, good? Okay, so, okay, on the old version of the APC, mass spectrometers probably constitute about, you see this scenario pop up about 10% of the time. Okay, where you shoot it through a velocity selector and then it hits this region where it's just a magnetic field and it goes in a circular path. Okay, very popular playground for free response problems. There's a lot of stuff you can glean from that scenario. Okay. So like we did that here. You set up magnetic force equals centripetal force and roll with it. And then magnetic force is equal to magnetic force and you roll with that. Okay. Okay, sure. Well, go ahead. Tell your neighbor. Okay. Correct answer is B. Conceptually, the larger the charge, the more force there's going to be pulling it in tighter, experiencing a greater acceleration towards the center of the circle. Okay. Mathematically, you get this. Magnetic force is equal to centripetal force. So you have magnetic field times the charge times the velocity perpendicular is equal to mass times speed squared over the radius. One of those speeds goes away, and you're looking for a radius. So radius is equal to mass times the speed over the magnetic field times the charge. The greater the charge, the smaller the radius. Good? So, great question. If it's not perpendicular, okay, so let's say it was shooting like this. That's still perpendicular. Is everybody okay with that? Okay. If it's not perpendicular, what it's going to do is going to do like a helix or a corkscrew. Does that make sense? Like it'll still do a circle with the component that's perpendicular, but the other part is going to make it that's going parallel to the magnetic field is not affected, so that's why it's going to spiral up or spiral down or wherever. Okay. So that's a cool physics demonstration. And they have some gas in there that gets eliminated when you shoot electrons through there. And these coils are making a magnetic field. Okay. Give that one a shot. Tell your neighbor. I'll just tell you. F. Stick your thumb in the direction of current. This is in an external magnetic field. So you're not doing right hand rule number 1. You're doing right hand rule number 2. Stick your fingers to the left because of these coming out of the page. Current is positively flowing things. Good with that? Okay. Tell your neighbor. There we go. C. Okay. This goes in. This comes out. Zero force, zero force. They're going parallel. So it's going to spin like that. That makes sense? This is how an electric motor works. You guys made an electric motor last year, a little floppy loop. Okay, tried to. Okay.
We're not doing that this year, right?
No. Tell your neighbor and tell them how you got there.
This right hand. So we got this coming up. We got this. We got this. We got this.
Correct answer is? Correct answer is A. You're doing the right hand rule twice. Sorry, no. You're doing two different right hand rules. You first figure out the direction of the magnetic field that this guy's making. It's coming out of the page up top where 1 is. So you stick your right hand rule number 2, stick your fingers coming out of the page, your thumb is the direction of this current, being forced down. Okay? 2 is going to be forced up. You could go through that same version, or you could say, oh, Newton's third law. Still a thing. Okay. That was a lot of words. We'll be all right.
Yay, he's gone.
Still rich.
No,
I'm disappointed in you.
Yikes.
Out of your
Can't do the problem.
Can you show me the problem? No, it wouldn't be serious. Oh, you're right.
This being question.
No. This is the force. This one is here. Just start rotating.
There's more current. Is it down?
Pretty sure.
I thought it was down.
Guys, I guess we'll never know what it is.
So it's like this.
Okay, correct answer is what? I agree with C. Okay. Here. Okay. So here, the magnetic field. Give me some colors. Magnetic field below this is going into the page, and it's getting weaker as you go away from it. Right? Okay? This guy's experiencing, the top one is experiencing up. This one's experiencing a force down, but the upward force is greater than the the downward force because the magnetic field's weaker. Here, these guys are experiencing a force that are decreasing, but these cancel out. You'd have to use calculus to like actually figure out how much force there would be. Yeah, good? Okay, here is your leftward speed zone.
But we were having such a good time.
I know. Okay. AP's review on Monday. I need to change somehow you can access. My favorite. So, I work on the lakes.
The biggest north part of it goes all the way along a highway.
So like multiple choice.
Bro, what
Yes, this was the I swear 16. Yeah, so I can just do it whenever.
Like, yes, there's no stop. The radio's going on, they're all one.
Isn't the two districts in Victoria?
I do that. Just write on the paper. What do you watch?
9 a.m. The game is 12. In Ed.
I got more.
No, I didn't.